All right. So as I mentioned earlier, when we have mass on a spring, it will tend to oscillate. So as you can see here, we've got this guy oscillating. Now this is somewhat of a chaotic oscillation because it's also swinging around. Ideally, we're going to have an oscillation that's only up and down, and that's pretty good. So we can see here, as it says, we'll give the mass a small displacement and see how it reacts to that. And that's the spring basically bouncing as it exchanges potential energy with kinetic energy as it extends and compresses. All right, so we'll record a data run of this mass bouncing up and down. We've set up Pasco accordingly. And let's just really quick auto scale these axes. Unfortunately, you're not having any luck in seeing what's going on here. Let me see if I can bring it a little closer. You'll get this data separately as well. Let's see. It's coming into focus. Yeah, you can see at the very edge there, it's starting to come in. I'm going to run a new trial so you guys can see how it looked like from the beginning. So I'll stop that. Give this one more little bounce there. Delete the last run, and let's record again. Maybe now you guys can see a little bit better the tracking here. Again, you'll get the data here separately, but you see how on the top we have the force, and on the bottom we have the displacement, and they're both bouncing up and down as you can see there. And we'll have that for you in a file for you to see those going on. So now we have that in question 3. It asks why these graphs are decaying. If you open up the data file, you see that there's really no appreciable decay in either the force or the displacement. Maybe I know that for the force, certainly there is a it's pretty large increments, so you can see very big steps between one force step and the next. And I think the data file we're including has maybe the first half of them with maybe one step further than the other. But again, that's not enough to be an appreciable difference. And what that comes down to is that the force that's damping the motion of that spring up and down is just air resistance. And this mass holder here, the only thing that's really appreciably being acting air resistance on is this flat bottom here, and it's pretty small. So for question 3, you can actually mention that there's not any appreciable decay with time, and that that would come from air resistance, but the air resistance is very small. So it's acting like there's no damping force whatsoever. By the way, again, the force that would decay these oscillations is called a damping force. Folks who are into sort of suspension will know that you've got not just it's not just a spring, it's a shock absorber that has oil flowing through. So that's what's called the damper of a shock absorber, which is what keeps the shock from bouncing indefinitely. So in this case, again, we don't have much damping force, so you can actually say that in question 3. Now, for page 2, we actually don't, we have another graph you'll see on your data, which is not time dependent, where we've just plotted how the displacement affects the force, or how the force affects the displacement, either one. And we can get a linear fit and get some information that's pretty important off that graph, because Hooke's law that we're working with actually is not a time dependent. One second. Okay, so just to show you what that graph is going to look like when we take time out of the picture, we've got this basically a scatter plot of with the position on the bottom and then the force on the side, and Again, since this is not time dependent and it's bouncing up and down and basically getting to the same position more than once, there are many different measurements for each of the position values and many different measurements for each of the force values. So that's going to be how we're going to get some calculations for our theoretical spring constants from that graph. And again, it's based on how the displacement changes with force. So to make things easier for you, we've already done the linear fit on the graph, and we've so you can see what kind of values we're getting from that spring. But it's your responsibility to interpret the linear fit to figure out what is the more meaningful values and what do they correspond with. So for question 4, you're going to want to take that linear fit and write it out using numbers and variables with meaningful units and correct significant figures so that we're not putting in too many or too few of these. So we'll just make sure to be careful when you do that, and we'll that's just an important part, so be sure to do that well. Finally, we'll move to data table 2, and we'll compare the two spring constants. We got one, the experimental one, the one we just did, and one, the theoretical one, the one we started off with, by measuring with the ruler and the masses hanging from our spring. From there, take the percent error between the experimental and the theoretical, see if they correspond, if they make sense. They should be pretty close. And we'll move on to part 2, which is springs in parallel and springs in series. So I'll just show you guys how to set this up for series and parallel. I'm not going to take the data. I've already done that. So you guys can just refer to data listed in the attached data document. So what I'm doing is I'm getting a spring connector here. This is just a little piece of metal with a couple holes in it to connect the springs to. And so when I have one hanging, then connected to another one hanging underneath it, then that's going to be those springs in parallel. And just to show you, we're going to add, springs in series, one after the other, my bad. And we'll add the mass holder with a 10-gram mass on it. And the actual mass right now doesn't matter so much because we're going to be using the force sensor to figure out what kind of a mass we're looking for. But as you can see, just the 10 grams has really pulled this much further than the 10 grams would with a single one. And just to show you what a single one would look like, I'll just connect this here. And you see it doesn't pull quite as far than it pulls with the two of them put together. So it pulls much more once you have two of them in series. Again, we'll have the data there for you to find the spring constant of this ensemble of two springs in series. And you'll put that into data table 3. You'll calculate the spring constant from there. And then finally, we'll also do this in parallel, where we have two springs working next to one another. And to do that, I'll take another one of these spring holders, and I'll connect the two springs again. And so now we're pulling both of them at once. And so you can see what kind of an effect this is. We're moving from just the mass holder with the 10 grams, moving all the way to a 50-gram mass on top of the mass holder. Connecting that, and you can see that it's actually doing a pretty good job of holding that back there. And let's see if we can, yeah, you can see that a little better here. If we now remove one of the springs, you can see that it will compress, extend the other spring much further than even I'm comfortable with. So I'm holding it down, but you can see that the two springs working together side by side are able to counteract that force more effectively than one all on its own. And you can imagine that in series, this 50 gram would basically send the springs to the floor. And again, we've taken data. You'll have to calculate theoretically what the spring constant would be with both of those working in parallel and both of those working in series. And very important little point here, folks. It says using the experimental value for question 6 for the single spring constant obtained in part 1. Again, make sure you use the spring constant that we determined using the Pasco linear fit, not the one we took by measuring with the ruler and the masses listed. So be sure to use that. Use KEXPT from data table 2 to calculate K theoretical for data table 3. That's all I'll say about that. And then compare for question 7 the percent error from what we measured using the linear fits in these setups compared to what we expect using the equations we used earlier on the blackboard for the addition in series or parallel for 2 springs. Finally, we'll get to the results and conclusions page. Now, we no longer have the sort of rubric set up there for you. So I expect that everyone will remember how we presented your results and conclusions, and realize that the graders will probably grade this. Certainly I will, the exact same way as we did in the rubric form. Basically 5 points per each of those sections. So we want a good fleshed out description of the procedure, basically what the goal of the lab was today, as well as a good presentation of the results you received. For folks in my labs, remember that I don't need all of your individual results. I'm happy if you just present me with one particular result that you came up with. However, other TAs, if you're not in my labs, may have already told you that they want all your results or some other combination. So go based on what your TA has asked you for. Again, for folks in my lab, you only need to present one. Since we no longer are held back by the rubric, feel free to present more because there's more space for you to do so now. But don't feel like you're expected to produce more results than you already have, than just one if you're in my lab. Now, finally, again, for folks in my lab, I do expect your sources of error to not only include the source, but also what effect it would have in the lab. And feel free to ask questions about what kind of sources of error we'd be seeing in this lab, because I think this one does have some probably, you do have a couple more considerations than you'd expect, because it may be harder to come up with ideas. So feel free to ask questions for the sources of error. Again, I'm presenting this lab, but your grader will be grading. So you know what your grader expects from you. So use those expectations to write your lab report, and try to just, if you want to consider how the rubric told you to use this section, just have that in mind when you're writing out the results and conclusions page. If you include basically everything you included previously and got full credit for or close to full credit for, and just adjusted what you needed to adjust, that's absolutely the correct path to take. And finally, for folks in my labs, again, I'm expecting you to have significant figures correctly represented, and units for everything, because I always take points off for not using units and not having the correct significant figures. So again, thank you for your understanding. This concludes lab number 6, Hooke's Law, and hope everyone's staying safe, healthy, and not too bored at home. Thank you so much. Take care.